Start presenting screen. Do you have any questions from the last lecture?
So
Yeah.
I had a question on the lecture on second.
Lecture on what? Sorry.
Uh, 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 Lecture that happened day before yesterday.
Oh, okay, okay. Yeah, go ahead.
Yes, so basically, we talked about refinement types and subtyping, right? So in
Mm.
refinement types, you mentioned that F star will be using the SMD solver to verify the types of sort, but for subtyping, it doesn't happen. Is it correct? So like reason I'm asking this question is like we created a subtype, sort of a narrower definition of factorial, which is from x is greater than 0 to integer, right? But
Yeah.
if you try to prove it using XML solver, it does snag, I think. So like it might not be the case that input for factorial function will be greater than 0. So say for example the input is 1, then
Mm.
the else part will get a call to factorial at 0. So if
Yeah.
you're going to
So
try to
let
verify it, it won't be satisfied, right? So
yeah. So what is your question? Let me just open up the slide so that we have some context. I understand what you're saying. I'll just open it up so that we have some context. Just give me a second. Um, so, this was okay. So this was let's see. So are you talking about this one here? No.
yes, sir. Yeah. So if you're gonna
Hmm.
try to do this verification for the other definition
Hmm.
that is a subtyping definition, I
Hmm.
think we might hit a snag.
Yeah. So the thing is, here we are sort of giving a type at the definition type, right? I'm actually saying nat or nat, and the proof obligation is the same as what we would have in OCaml, right? So if I just said, oh, this factorial function takes a string and then returns you a unit value. So because you explicitly said, say n is a string, OCaml is going to complain, oh, you told me n is a string and you're now comparing this to 0. So I'm going to fail. So you have to look at the body of the function and then do the usual type inference, type checking, but also discharge some constraints to the SMT solver where we actually gave the subtyping, right? So this one, right? Here, we only have the definition of the factorial. Sorry, we just have the name factorial and the type associated with it, right? We actually don't look at the body of the factorial. So that's why the subtyping sort of, Deepali had a question which we sort of saw, right? Even though we might have a more precise specification, if we don't have the body at the type checking position, we can't do anything. I mean, F star cannot do anything because it will be an arbitrary function. We just apply the direct rules of subtyping, which is the subtyping rule for functions. And if that holds, it holds. We can't do anything more. As it sort of, is that the question that you're asking first?
Yes, so I just want to add on to it. So like,
Hmm.
if you, I mean, I just want to first, I want to confirm that if we try to prove this type using the
Hmm.
definition, we won't be able to, right?
Uh, if we try to prove this type, oh, you want to prove that, oh, okay. I see. So what if I gave this type, right? So for this definition is what you're asking.
Yes, sir. Yeah.
Okay, good question. So yes, because why don't we try that? Actually, I don't know the answer. Let me switch to the previous one, start functional, and then really good question. So let's try this out. So we have the factorial function which is nat to nat, and then we have this type. So let me copy this type. Um, yeah. So this type holds for factorial. Let's try to assign this as the type for factorial. Factorial is this type, and let me delete this. So what is that? What is our expectation at this point, right? Will it go through or not? Um, what do you think? What do you think will happen?
I think it won't go through.
Okay, let's try. So sorry. So this is I should be, it doesn't go through, not because of n equals 0, right? It doesn't go through because I can't now prove that this particular value, right, is not greater than 0, right? So because I said it could be any natural number, right? The input contract says that it is any natural number that is greater than 0. Although I have n equals 0, if n equals 0 as a condition here, right? Subtyping actually works. I sort of say, okay, I am just using equality here. I know it cannot be the case that n can be equal to 0 here because I'm always saying this n is greater than 0. So all SMT solver is will try to do is to so there is a distinction, right? If you say something wrong, SMT solver will actually try to try to shout at you, right? It will essentially say, "Oh, this squiggly line will appear and say type checking does not go through." But if you give a case which doesn't apply, so these are known as cases. I mean, this is a case which cannot be taken, right? That's the distinction here. Even though I have n equals 0 here, I can still do the equality because n is still a natural number, right? The subtyping still holds. So I can still compare it, but statically SMT solver knows that this case will not be taken, right? Because n cannot be equal to 0. But the definition fails because the type checker cannot prove. It knows that n is x is greater than 0, right? This input is greater than 0. But when I do n minus 1, it might be equal to 0 because 1 is greater than 0. 1 minus 1 is 0, but that doesn't satisfy the input contract. And hence, this particular recursive call type checking fails. You see the distinction here, Vishnu?
Yes, yes. So I actually want to exaggerate
Yeah.
this. So like given that we were able to prove this is a valid type of factorial
Mm,
using subtyping, but we
mm,
are not actually do it during the definition, like
mm.
does it kind of make subtyping wrong or something like I
Okay. So you're asking, so even though we were able to give this type, um, what is the, um, why do you call it wrong there? Let's just expand on that, right? So let's see why we would call that as wrong. So okay, so this type works out, but we cannot type check this function with this type, right? Um, so what does that mean? So okay, so let me put it this way, right? So let's write out both of those types down. So what does subtyping for function mean, right? So um, basically, let's start from here. When I write this, right, what does this actually mean, right? This basically the subtyping relation here says that wherever I expect an integer, right, I can pass a natural number because every natural number is an integer, right? If you sort of apply the same rule for this type, right? Um, nat arrow nat. Is that the right way? Yeah, that's the right way. Is that the right way? Um, let's no, the other way. Sorry. Subtyping are always a little bit tricky. Um, so let me write this out here. So let's extend the same analogy, right? This says that wherever I expect an integer, I can pass a natural number because every natural number is an integer. So what this says here, if you apply the same thing, is that wherever I expect a function argument, right, where the expectation is that that function should accept values greater than 0 and will give you a value that is an integer, I can pass this function at that point, right? Because this function is going to be in a context where it will be passed values which are always greater than 0. So this function can handle all of those values because it can handle integers. It can handle natural numbers, right? So any context where this function is expected, I can always pass this function as the input for that. So what does this function say? This function may be used in a context where it is the inputs. The only valid inputs are 1, 2, 3, 4, 5, 6, 7, 8 up to infinity, right? And can I use this function in that slot? Yes, I can, because this function can handle 1, 2, 3, 4, 5 up to infinity, but it can also handle the input that is 0. Right? That's the expectation here. And this function says that function which I expect should return an integer. And can I use this function here? Yes, because this function always returns a natural number, and any natural number is an integer, right? And hence this particular function, this nat or nat function, can be used in a context where this particular function type is expected, right? So that's the way you should look at subtyping here. So subtyping is useful to automatically discharge the constraints where you sort of fill a hole, right? The if the hole is a integer, can I fill it with a natural number? Yes, every natural number is an integer. Similarly, for functions, if the hole is this function type, can I fill it with this function type? Yes, we can, because our subtyping rule says so. Does it sort of give you an idea, Vishnu? It's sort of, this is why I mentioned that subtyping is a little bit interesting. But we will look at more example, I think, when we study lambda calculus. There will be one assignment on subtyping later in the lecture, and I think we will study it there.
Yes, so just yes, yeah. So like just that the arguments of the flipping of the arguments of the inverse makes a bit tricky, but I get your point. Yeah.
Yeah. So it's the way you have to sort of look at it is not. It's just that, can I supply a type where another type is expected, and you can supply the type if the type happens to be a subtype of the expected type, right? And that is exactly what is happening here. Can I get this function? Can I what sort of functions can I fill in a hole where this type is expected? I can fill in any function that is a subtype, and this function happens to be a subtype. Really good question. I think you should. We will come back to this later in classes when we study subtyping. But it's if you don't get confused on this particular topic, at least have some question. You may be missing the subtlety. And thanks for asking this question. I always get it wrong the first time. So we will study this again in subtyping, and you'll have a assignment on subtyping. So you'll have enough opportunity to actually be a lot more confused and get clarity about this. It's actually a very beautiful concept, this subtyping for yeah, let me go on a rant, right? So subtyping is a concept that is actually pervasive, right? So this nat and integer is one. This function subtyping is another one. There is also subtyping when you have um, subclasses, right? Inheritance in object-oriented world. So you can imagine we've done this, right? So you have say a shape, right? Maybe a shape has a color, and then you can have a subclass which inherits the shape class and says the shape is a square. So the square might have a color as well, but it also has a notion of a side. The same shape, you can also have a circle, right? And that has a radius that describes a circle, but also has a color. The question that we are here dealing with here is functions, right? Which is what makes it a little bit tricky. It's not just like a single value. So this relationship between a shape, a square, and a circle is the same as what you have with non-function types. But there are some interesting aspects when you actually have to deal with say a list of shapes, and what sort of list of shapes and things you can do. We'll study more about it in subtyping. I think it's perhaps too early to get into the details. But all of these are connected, right? So the subtyping is in practice in object-oriented programming very much, right? Whenever we use inheritance, we are actually doing subtyping. Anyway, so with that, let me move on to the next lecture, which is on, yeah, okay, beautiful. Yeah, I might keep on going ranting, but that's okay, right? So it's a small class, so let's go on ranting. So let me open the other file. Okay, no branches. Okay, this I'll just not save it. It's okay. So okay, so what we are going to do in this lecture is, so we've sort of touched upon this topic of verification, right? We've said we have this notion of verification. We can write small proofs, but really what we want to do is to actually prove interesting properties, and the properties may be more complicated than what we can just describe using refinements that we associate with the input and the output type of functions, right? And broadly, you can sort of split this into two approaches for verifying using F star, right? And the first approach is that what we've done so far is to intrinsically describe the constraints as part of the refinements on the type. When we said the factorial function takes a natural number to natural number, it's actually a refinement on the integer input, right? It says integer where integers are greater than or equal to 0 as the input, and integers where integers are greater than or equal to for the output. So that we call as intrinsically at definition time. And during type checking, we sort of go ahead and check whether the constraints hold. You can also do extrinsic verification using SMT backed lemmas. I mean, this is what we are going to see in this class. The idea here is that you might have some properties which you describe about a function when you define it, but you might want to describe more properties about the same function, right? I have an append function. I can say something about append, which says something about the length of the length of the result list and its relation to the lengths of the input lists. But I might also want to say something about membership as well. So all of the other properties, right? You don't want to always associate all the properties with the at the definition time. It just complicates stuff. So we might want to prove additional lemmas as a separate way of doing it. This is the only way to, I mean, this is what we've done in Coq, right? We always write the definition and we say, okay, let me prove a theorem on this particular function. And that is what extrinsically doing proofs in SMT is all about. Let's actually look at what they are. So here is the factorial function, right? So we wrote nat arrow total nat, right? Again, totality is an effect which says that it always terminates and doesn't have any other effects. So this, when we write this function and compile it, all we are doing is we are intrinsically verifying that factorial satisfies the natural number expectation. I mean, it satisfies the theorem that for every input that is greater than or equal to 0, the output is also going to be greater than or equal to 0. But we can also equivalently write this as very explicitly using this type definition. So the way to read this type first is factorial 2 is the same as factorial, except that it says the input is, I'm going to give this input as x, and x is an integer, right? And the output type is this whole thing that sits here, right? And the way to read this is that it is an expanded form of what is known as a refined effect type. And the effect type says that it's a pure effect. You can sort of read pure as no other effects and also terminates, right? It is going to return an integer, right? Factorial 2 is going to return an integer, but there are pre and post conditions on this function. The precondition requires that x is greater than or equal to 0, which is the same as what we are describing here, right? When we say the input is a natural number, and the post condition says that this is actually a higher order function. This is a lambda, right? So the result of this is applied to this function. So y is the output, and the post condition says that y is also greater than or equal to 0. Right? So actually these two types are equivalent, right? I mean this goes through. In fact, whenever we write dot, right? Whenever we write dot n, dot t is basically syntactic sugar for pure t, a pure computation which returns a t value as a result, right? A type t as a result, and then no other preconditions. It doesn't say anything about precondition. When this top is just true. When you write oops, when you write capital T R U E, you just get this top symbol. It just says no precondition. It's just true, and ensures says something about the post condition. The post condition here says that it's simply true. So it doesn't explicitly say any pre and post conditions. Precondition is true, post condition is true. And whenever you write dot t, you are actually, it internally expands to this definition, right? But again, the whole point of doing this is you can have very rich pre and post conditions. We will see what they are. And similarly, this dv that we saw, the divergence that we saw for interpreter for lambda calculus, right? Is simply a syntactic sugar. Whenever we write dvt, it is actually the effect div effect. The computation is going to return a value whose type is t, and the precondition is true, and the post condition is also true, right? No other post conditions explicitly stated. So we might use dot and div a lot of time, but internally they are just syntactic sugar for explicit pre and post conditions, right? And again, this requires, the word requires and ensures are actually just there for readability. You can drop them if you want, but I recommend keeping them just to show that they are just they are not necessary. So the type that I have here, right, is the same type that I have here, except that I've dropped the requires and ensures. So I can just write it as factorial as pure is going to return a value which is an integer with the precondition that the input x, which is here, is greater than or equal to 0, a natural number, and the output y, it's a lambda, right? So this thing is going to be applied to the output value. So the output y is also greater than or equal to 0. But I recommend keeping, if you ever happen to write explicit pre and post conditions, I recommend keeping requires and ensures just so that it enables readability. Okay, so that also goes through, that compiles. Oops, yeah. So I mean, we had this very simple world of types, right? And then we said refinement types, and then I said something about fx, and I say now something about refined fx. So what is the high-level view of the type system in F star, right? So the type system in F star can types in F star can be considered as belonging to what are known as two different kinds, right? Kinds is a technical term. Essentially, the type of types is known as kinds in the programming language literature. Maybe this is the last time we will use kinds, but know that kind is a technical term, not just like something that I picked out of thin air. So we can view F star type as belonging to two kinds. So there are two kinds of types. The first kind is a value type. A value type is an integer list, actually integer list, string, boolean, and so on. And then we have computation types. The computation types are dot t, divergent t, and so on, right? So so those are the two main types. And of course, you can refine both of them. So you can have refined value types, right? You can have a value type t such that you have some predicate p associated with the type, right? You can just give a name for that variable, and then you can define a predicate, a very rich predicate. The predicate could be any total function, right? And similarly, you can define the computation type. Recall that dot t and dvt are really pure and div with pre and post conditions. Again, this pre and post conditions can be very rich, right? This precondition and post condition can be any total functions. You can use any total functions in your program. right? It's very, very rich. Everything is sort of allowed there. So you can refine it further using the explicit notion of pre and post conditions. So you have these two basic kinds, which are value types and computation types, and you can refine both of them. Okay. And then we also have dependent types. Dependent types we've just been using all along. So essentially, when you write a function, which is x0 arrow, x1 arrow, x2 arrow, x3 arrow, up to xn, and then returns a computation, right? Recall that every return type of a function is actually a computation. If it doesn't do anything interesting, we just call it a total computation. It doesn't have any effect, which is a pure computation. But every function type sort of fits this pattern, right? And what are dependent types here? For x0, you can have the type t0 with some refinement possibly. For x1, the refinement can refer to x0, right? And similarly for xn, the refinement here, the thing that appears within the brackets can refer to all the previous variables as free, right? So they are all in scope. So you can say something about x0, x1 in say xn, where n is greater than 1. So these are known as dependent types. We've seen dependent types already with that increment function. They are dependent because the type here, this type here is dependent on the value. Observe that x0 to xn minus 1 is actually the value that is input to this function. So because the type is dependent on a value, we call them dependent types. And this is the generic signature for the dependent function type, right? So at the from a high level, right? So that's the view of the types that we have. We might not actually delve too deeply into each of these types. We will worry more about proving than studying these different classifications, because that's not useful. I mean, the classifications are sort of useful for forming a high-level picture, but beyond that, it's how you use them in order to express interesting properties. That's quite fun. Okay. So yeah. So I mentioned, I mean, the whole point of this lecture is there is this very two ways of verifying functions, right? One is this intrinsic verification and another one is extrinsic. Let's do the same proof both intrinsically and extrinsically. Okay. So here is the length function that you might define on a list. So a length function takes a list of alphas, right? And it returns a natural number, and the computation is a total computation. So it always terminates and returns a natural number. So that's great. So that's the length, right? And you can write a very nice specification for append. You can say append is a function that takes a list L1, which is a list of alpha, list L2, which is a list of alpha, and list L3 is a list of alpha. And the refinement here says something very rich, right? It says that the length of L3, the result, is equal to the length of L1 plus the length of L2, right? And that's the specification that I have for append. And the definition itself is the same as what we had written in OCaml. So there is no result. And if you let it give it to F star, it will automatically go ahead and prove it. The point I want to make here is recall how we did list append in this append of lists which are length indexed in OCaml using GRETs, right? We had to explicitly construct this proof of sum of natural numbers by hand, because OCaml does not have a SMT solver that is backing it. But once you have an SMT solver that is backing it, you can actually go ahead and write like rich specifications like this and get automatic proofs. So now the thing that you have is that this append function is going to give you some list, right? It doesn't say anything about the elements, but the thing that you know is that the length of the list is going to be the sum of the length of the input lists, right? And that comes absolutely for free. And that's the power of doing SMT back proofs. Recall that we did the same thing in Coq. We had to manually reason about, we had to do some manual reasoning, right? And that manual reasoning is what we can choose to do with extrinsic proofs. So here is extrinsically verifying append. And the idea here is that we are just going to write append as we would in OCaml without this refinement, right? This refinement explicitly here. And we are going to write a separate lemma and then prove that this same property holds. Okay. How do we do that? So I define an append to, right? Which just says that I take a list, I take another list, I return some list again. I don't say anything about the relationship between the two input lists and the output list, right? And those are defined here, but none of it is defined here. This is the type that we would have in OCaml, right? List append takes two lists and returns a list which has whose elements are the same. The definition remains the same, right? But we haven't actually proved the property. We haven't actually mentioned the property that the length of the result list is the sum of the length of the input lists. How do we do that? So when we write extrinsic lemmas, right, the only thing that we have, just like Coq, right, there are no fancy things sitting around in these languages. At the end of the day, everything is just a small function with some syntactic sugar to make it look like you're doing proofs. But really, everything is just a function definition. So our theorem and proof here simply adopts Curry-Howard correspondence. So what we are going to do is to define a function whose type represents the theorem that we are going to prove and whose definition is the proof of that function, right? So append len here, you can sort of imagine this to be a theorem. Even though this is just a function, this is a theorem. And what does the theorem say? It says that take a list L1 and another list L2, right? And this theorem, because it's only going to prove properties, does not return anything useful. So it's a pure computation that returns a unit value. I don't have any preconditions on the inputs, right? But the post condition says that the length of appending L1 and L2, right, where append is this function, right, is equal to the length of L1, this L1, and the length of L2, right? So the analogy here is this is what we would have written as theorem in Coq, right? But we just use the syntax for function signatures and function definitions in order to write down this particular theorem. So this is just the theorem statement, right? And again, Curry-Howard correspondence, right? In order to prove this theorem, we have to write a program that is the proof. So what is that program? So here is the program. I'm going to write a function, and that function append len takes two input values, L1 and L2, right? And if you sort of imagine how we proved things like append and so on, we sort of looked at the structure of the program, right? And we said we will do case analysis or we will do induction and so on. And in Coq, we use tactics in order to build up the program. F-star also has a very rich tactic system, but even without going to tactics, right? We can build proofs using SMT solver very easily. Okay, so that is what we are going to do here. So the way to prove this theorem is by induction, because we are going to induct on L1, and we are going to say there is a base case, there is an inductive case, and the way you actually do that is by constructing a program, and here is how you do it, right? So L1 and L2, I'm going to induct on L1, so I'm going to pattern match on L1. If L1 is empty, I'm just returning a unit, right? This would seem very, very, very strange at the outset, right? But bear with me now. So what is the expectation? Why am I just returning a unit, and how does this prove this theorem, right? Firstly, L1 is an empty list, right? And um, what is the actual requirement that we have for this function, right? The requirement is the output type. The output type says that I need to get a unit value as a output. So that's fine. That's easy. And I need to ensure that the post condition of calling this function satisfies this property, right? This thing that I've written down here, right? And where particularly L1 happens to be an empty list, right? So let's just go with that, right? We need to show the post condition, right? This ensures. Let's see whether that holds. So the length of, I'm just writing this down where I substitute for L1 this empty list. So I substitute for L1 this empty list, right? And observe that append to of empty list L2, I can just go ahead and look at the definition and do the substitution, right? So SMT solver actually goes ahead, looks at the definition, and then does the substitution for you. So here, if you sort of look at the definition of append to takes two lists. If the first list is empty, it just returns L2, right? Just by applying simplification. So we would apply the simplified tactic here. Just by doing simplification here, we know that this term here reduces to L2. So this whole term on the left hand side is just length of L2, right? And what about the length of empty list? So I'm going to split the screen. I'm not doing anything fancy. I'm just splitting the screen so that I can show multiple things at once. So observe the definition of length, right? And what we want to do here. So the length, if the length is empty list, it is just going to return 0, right? So the length of empty list here is just going to return, 0 here, right? Okay, so this was obtained just by simplification, right? We just went ahead and did simplification and arrived here. And what can we say about this? Now we have some arithmetic, and we also have some function length, right? And we have some arbitrary L2 here. The way to read this is for all L2, right? The SMT solver is now has to show that length of L2 equals 0 plus length of L2. And SMT solver has this notion of uninterpreted functions. As the name suggests, right? Uninterpreted functions are just regular functions. They behave like functions. If you have the function and you give it some value, if it returns some result, if you give the same value again, it returns the same result. So you can sort of think about this length of L2 as just some term v, right? And similarly, because the length behaves like a function, this length of L2 is also v. So the proof obligation at the end of the day that is given to the SMT solver is that for all v, show that v equals 0 plus v, where v is an integer. We know v is an integer thanks to the type. And this is easy, right? Because 0 plus v equals v is just the theory of integer arithmetic, linear arithmetic, right? And that is what SMT solver can do very nicely. And this, the post condition happens to be proved. And that is why we are just able to say unit here. And that is enough for proving the post condition. So even though I'm writing all of this down, all you need to write here is just unit. And the fact that SMT solver does the simplification for you and goes through all of these motions is behind the scenes, right? This is what the advantage of having SMT solver is. But I would also call it the disadvantage, right? So how do you actually know what is true at this point, right? And this is where proof engineering comes in. So when you sort of do proofs with Cog, everything is explicit, right? Cog does not help you at all in the sense that it sort of, even trivial goals, it just shows you and you have to apply trivial in order to make it go through. But here SMT solver is doing a lot of work, but sometimes it will get stuck. So one of the nice software engineering trick for proof engineering in F star is that you can use assertions. Observe that assertions are static in F star, right? So you can just write an assertion at some point in the program to query what is true about the program at that point. So here are some assertions, right? And the way to read this is I'm going to return a unit, but I'm just having some statements here where I'm asking F star, does this thing true? Is this thing true at this point, right? I'm asking whether in this context, the length of append of 2 of L1, L2 is equal to length of L2, right? And SMT solver will return true, right? It will say it is true because in this branch, in this case, I know that L1 is empty. So this must be true. And I can also ask whether length of L1 equals length of L plus length of L2 equals length of L2. This is also true because length L1 is an empty list here, right? So that will go through. So actually, this whole thing goes through. Let me come to the inductive case. But that's the way you sort of, if the proof fails, you can add assertions to find out what is true from the context. So the context has a bunch of assertions. You can query the program to know what is true, right? And here I've queried a certain things. I'm just asking whether this is true. Of course, if you give something wrong, yeah, so SMT solver will come back and say this assertion has failed, right? It doesn't tell you anything more. It doesn't give you a counter example or anything. It just tells you the thing has failed. But if you can start debugging it by asking these simple questions. I I mean this is very important when you actually prove bigger programs in F star, where you sort of start with very simple notions of what you understand is true, verify that that is true, and slowly build it up. Right? All these assertions are sort of helping the proof as well, for you to convince with the help of F star to know what is true about the state of the program. Okay, so that's the base case. It's surprising how just unit here does all the work for us, but that is what is happening underneath. So what about the inductive case, right? Again, just to remind you what we are doing, we are proving that length of append of L1 L2 is equal to length of L1 plus length of L2, and L1 is now a non-empty list, right? So it has a head and a tail, X and XS. I need to prove the inductive case. So what do I know? Let's start with what we had done earlier, right? We will just substitute for L1 this term, X cons to XS, and then see how far we get with simplification. So we can do the substitution here. If you just do the substitution in the post condition, the thing that we actually want to prove, you will just get this term, right? Let me open the second. Oops, why is this getting stuck? So let me open uh, the second terminal just to show progress. So how does this simplification work? So first thing is we want to simplify what append to does, right? How does append to work? So let's look at the definition of append to. Let rect append to. So if you look at append to, what does it do? If the list L1 is non-empty, the thing that you get back is X cons to append to of X is L2, right? So this term can be reduced to this term just by simplification, right? And now can we proceed further, right? So look at how length works. So I have a length of X cons to some term, and similarly length of X cons to some tail, right? And this is a universally quantified term. I can't do any reductions there. So let's look at the definition of length, right? So val length. So if you look at length, if the L is non-empty, so this case, it's just the 1 plus the length of the tail, right? So you can reduce this term to 1 plus the length of the tail. The tail is this term, right? This whole term. And similarly here, it's 1 plus the length of XS, right? So we've done all of the simplifications. Actually, we can't proceed any further here because all of these are universally quantified. This is universally quantified. This is universally quantified. So what is actually missing here, right? I said the inductive case. We haven't actually applied the induction hypothesis, right? So how do you apply the induction hypothesis? So in Cog, what we did is we get the induction hypothesis as part of the list of assumptions, and we said, oh, apply the induction hypothesis or use it to rewrite. So here, the way you sort of get the apply the induction hypothesis is to actually call this function. So this is basically a function, right? What we are defining is a recursive function. I mean, this is the duality between recursion and induction, right? So I know if I call this function, the thing that I will get back as a post condition is this, right? and there is no precondition. So what I'm going to do here, in order to introduce the induction hypothesis, I'm just going to call the function that I'm defining, function that I'm proving on the tail of the list xs and L2, right? So when I call this function with xs and L2, because of how induction hypothesis works, I get this induction hypothesis in my context, right? Where L1 is now substituted with xs, because that is what I call that function with here, right? So what have I got as a result of calling it? I get the induction hypothesis, which is this: length of append 2 of xs L2 equals length of xs length of L2, right? Where L1 has been substituted with xs. That is all I have. So now, right? Now it becomes very standard, right? So I know this is true thanks to the induction hypothesis, and with this assumption, I need to prove. So this is logically entails, right? Or you can, the Coq way of doing it is to write a long bar here, but we just write it as a short form here. So under this assumption, I need to show that this holds. Where does this come from? This is just the thing that we obtained earlier, just by simplification, right? So now you can do the usual thing, right? You can just do this rewrite. You take this thing, you rewrite it with this term, right? If you rewrite it with this term, you'll just have 1 plus the same term, and there are some theorems about commutativity and associativity, right? Actually, yeah, commutativity and no commutativity, just associativity. Um, Again, this associativity is a property about integers which the SMT solver knows. So that whole thing, hence the proof goes through. So all I've done, even though I've written so many comments, right? If you just look at the proof, all I've done is I've pattern matched on L1. I said for the base case return unit, and for the inductive case, just call the uh, function again on the tail of the argument in order to get the induction hypothesis into the scope. That's all I've done, right? And with that, the whole function is proved. So that goes through. So I mean, one can argue, right? So as if I can write the proof directly, just like this, why bother writing this explicit proof? There is a reason for it. We will sort of you will observe that it is not always possible to intrinsically prove functions using F star. You have to use extrinsic lemmas, and it is also not useful because if you want to prove everything about a particular function at the definition time, you have to go back to the definition and like um, make it larger, which just complicates all of the nice properties that you have just by having succinct types. So extrinsic lemmas are useful. It is also useful to know how they work. And what I've shown you is how extrinsic lemmas work where we apply induction hypothesis. Okay. And yeah, the last thing that I want to say is that so if you just look at the type of the thing that we've written down for the theorem, right? I said pure unit requires true and ensures length of this thing. So in all of this, right, the only interesting thing here is this one. All of the other stuff from here to here is just craft, right? So again, F star has some syntactic sugar in order to write the lemmas in a nice way. So you can just write types, the output types of functions as lemma post condition. And when you see lemma post condition, it simply expands to pure, returns pure computation that returns a unit value. There is no precondition, and the post condition is just the post that you give here. And similarly, you can write lemma pre-post, where it's a pure computation, returns a unit value, requires a precondition, and ensures the post condition. So again, we can rewrite this whole function using this lemma syntactic sugar, such as this one. So let rec, right? L1, L2 is a list of alphas, right? I'm not even writing val explicitly. I'm just writing it as a function. And the thing that it is going to return is a lemma, right? where the length of append 2 of L1 L2 equals length of L1 plus length of L2. All I've done is I've just used this syntactic sugar here. The proof still stays the same, right? I am applying induction hypothesis. I'm proving this by induction. I am, for the base case, you just return unit, and by simplification it goes through. For the inductive case, you have to explicitly apply the induction hypothesis. So one thing that F star doesn't do automatically for you is to apply the induction hypothesis, right? So if you want to apply the induction hypothesis, you apply it by recursively calling the same function on the smaller argument. So that becomes part of the context with which the SMT solver can prove the theorem. So that's that the proof goes through. So if you delete all of these comments here, you will end up with the same thing. Yeah, okay, wonderful. So what I will do is I will stop here, and yeah, what you'll see is you'll see a lot of comments, right, that I associate with these things. But it's useful to know how these comments work, because the proofs themselves look very like surprisingly simple, right? But there's a lot going on behind the scenes. The whole point of the course is to understand how these behind the scenes things work. So yeah, so there's a bit more left about why we want to use extrinsic proofs. Sometimes these sort of extrinsic proofs are unavoidable, which we'll see on Saturday class. And yeah, and I hope that we can finish the rest of the lecture on Saturday. So I'll see you on Saturday. Thanks for taking time off weekend and then appearing for the class, right? I really don't recommend people to work on weekends, but thank you for yeah, so showing up for class. And if you don't show up, that's fine as well. You can look at the videos and then ask questions later. Okay, great. So I'll stop here. So we'll meet on Saturday. Thank you very much.